the idea that we have now developed is that we're doing this ODE analysis, this differential equation analysis. We're trying to relate rates of change of heat transfer, right? So dq dot dx or whatever, to something that's happening in the domain. So in generation, it was dq dot dx is some constant, right? And that constant or position-dependent thing was given to us by like a volumetric generation constant. For extended surfaces, it's a little different. So now we're going to say we're still going to model a 1D system. We're still modeling heat temperature gradient in only one dimension, but now things are happening that are actually a function of temperature and not just position or not just a constant. Okay, so this lecture is, I'd say, like the peak of math trouble. So, like, if you've been annoyed with math so far, you're going to be really annoyed today. But I will promise you it gets better, right? So this is kind of the top of the hill. And then from this point on, we're going to be talking about numerical methods, which are really mathematically easy. And we won't really go much further in this class than this level of difficulty, okay? So if you can hang with it today, you're in good shape. All right. By the way, if you haven't been able to hang with it so far, that's okay too. So office hours are a thing, and you'll get through it. Okay, so extended surfaces. Let's first of all, yeah, this is what I just said. So extended surfaces, I want to think about what I mean by an extended surface and what the special conditions are for this model. So like I said, in the modeling we've done so far, we have this maybe example that we started with from other times where we have conduction in this x direction. We don't have any conduction in this direction. So when we drew our domain, we're drawing this like, vertically stretched but differentially thin in the x direction control volume. We do our analysis on that. And then we notice that these surfaces here at the top and bottom, right, these are adiabatic. So there is actually no heat loss as we're going through the domain. So an extended surface is basically the same starting point, but we're now allowing heat to flow out. So think of examples would be like a fin on a computer heat sink or something. Maybe think of it this way. So like a piece of metal, like a long shelf. You are conducting along the length, the thin length of the shelf, right? You can see the table. So we're conducting in this direction, but there's heat being lost from the top and bottom of the table as you go along. So the whole idea of the extended surface is we still want to just model the temperature profile along the thin, like this long direction of the table. We want to neglect the temperature gradient through the thickness of the table, right? If we can do that, we can simplify the modeling. Okay, so I'll maybe try to say that again a couple times so you understand it. But the basic idea is this. So we're going to go through the analysis, and if you looked at the actual temperature profile in, like, say, an extended surface, you're going to see some certain characteristics. So let's say we have some fin, oops, like this. We have a fin in it, and we're forcing heat into the base of this fin. So the base of the fin's on the left. The top, bottom, and the sides we see into and out of the page are exposed to air. And we're sort of forcing heat to go into this fin. If we're doing that, and we looked at the temperature profile at these different positions that I've drawn here, what would we see? Well, we know that maybe as you go further down the fin, in this direction here, as you go further down the fin, you're losing heat, right? So the temperature is going to be dropping a little bit. But you also know that there's heat going out the top and there's heat going out the bottom. So if you sketch the temperature profile, it might look something like this. So let's pick this one. So this is my coordinate system, so I'm going to say like this is my temperature axis. And then the sort of vertical slice is the position. So temperature might look something like this. Right, so this is outside the domain. Let me do that. Sorry, I'm going to do it like this. Like this. Right. So what did I just draw? So you have a temperature profile. If you look at that particular location, this is the temperature in the vertical direction. Okay, hopefully that processes. As you go further down the fin, you lose heat. So what is this temperature profile doing? It's kind of shrinking a little bit, right? So I'm saying that this dimension here is getting smaller. So we're losing heat. And that's fine, right? That's good. The whole point of the extended surfaces analysis is I don't want to do a 2D model, right? This is a 2D temperature profile. You have temperature dependence in x, and you have temperature dependence in y. Let me be clear about my coordinates. So this is x, this is y, this is z. I have a temperature dependence in x and y. I don't want to do a 2D model if I don't have to, because they're difficult, right? It's computationally expensive. So I want to do a 1D model. What are the requirements for a 1D model? Well, I basically have to prove that there's no significant temperature gradient in the y dimension. So what I'm saying is, if we had a temperature gradient that was basically this, and then basically this, right? That's a 1D model. There's no y dependence of temperature. So I can get away with just a 1D simple expression for that. Okay, so if we're all on the same page there, I'll kind of tell you how we get to this point. All right, so let's go to the next slide here. So there is a computation that you can do to justify this 1D assumption. And it is called the Biot number. So B-I-O-T, not B-O, just B-I-O-T. Biot number, again, a French person. And the idea is that you're trying to relate two quantities to each other, right? It's a ratio of two quantities. So if we can prove, like I said, that there's a delta T inside the domain, so let's call this delta T due to conduction. If I can prove that that delta T is small relative to the delta T to the surroundings, delta T surroundings, so if that's, let's say, less than 0.1, then my assumption of 1D temperature profile is reasonable. Okay, so the Biot number calculation says compare basically the two temperature differences if they're small, or if the internal resistance or internal temperature drop is small relative to the surroundings, then it's good. And so like look back at this for a second and let's think about that. So I'm saying here, on the green line right here, there is no temperature drop at all. But in reality, maybe there is a little bit, right? So it kind of comes down like this. You can barely see it, but it kind of comes down like that. So I would say this little delta T, right? That's my delta T conduction internally inside the domain. That is small relative to, maybe I'll draw it in blue, right? This delta T here, right? So this would be delta T surroundings. Sorry, to be clear, it would go to the internal line, like this. Apologies. Like that. Right? So if you can prove it's small, then you have a 1D model. Okay, so that's the idea. So let's give you a more concrete definition of the Biot number so you can actually compute it, and then go through an example. So we know conceptually it's the ratio of two temperature differences. What that actually means is we can look at, this, we'll abbreviate it BI, so Biot number is BI. Let's look at the ratio of resistances, because remember, resistance is going to be proportional to the delta T. So let's look at the resistance in Y divided by the resistance to the surroundings. Okay, so if we can compute those two resistances, we don't need to know temperatures, just compute the resistances, it gives you the same information. And again, this should be, normally we say much smaller than 1, but that to me usually means 0.1. In practice, like you have to make the decision what's good enough, like what is reasonable. But for this class, if I say, prove it's smaller than 0.1. Okay, so let's do this example. So we have a Biot number. For this example, this fin that we're looking at, we need to compute our conduction and the Y divided by our I guess, let's say we just have convection. So R convection. So the fin is convecting to the surroundings. Let's neglect radiation for this problem. So we know how to compute these resistances. The tricky part is like thinking about the areas and things like that. So let's start with our conduction Y. So remember the conduction resistance for plane wall is thickness over K times AC, like the cross-sectional area that's available. So if we're thinking about conduction resistance in the Y direction, right, we're not talking about conduction resistance down the length of the fin, it's in the Y direction. So what I would want you to do is maybe pick a point of symmetry. So let's pick a point in the middle. Let me be clear here. So maybe more towards the base, just to show you which middle I mean. So the middle along this line here, right? So you're right in the middle of between the top and bottom surfaces. And heat's either going to flow up or down. It's not going to cross that symmetry line. So you have this point in the middle, and then we're going to look at how heat can get out. So heat's going to either go down or up. Let's just pick one direction because it's symmetric. So I'm going to draw a line like this. So it's going to go up. So I'm going to look at all the resistances that kind of are involved in that direction. So starting with this R conduction Y, what is the resistance to heat transfer in the Y direction if you're a bit of heat at that middle line? Right? So that's going to be the distance to conduct. What's the distance to conduct? It's actually thickness over 2. Right, thickness over 2 is my distance to conduct. So distance over K times A. So in the denominator, let's say times K, the material conductivity, times A, so the cross-sectional area. What is the cross-sectional area available for heat transfer in the Y direction? Can anyone see it?
W times L.
Yes. W times L, right? You see why that is? It's the area available in the Y direction. Be careful about that. Okay, so that's our conduction inside the domain. Our conduction to the, or our loss to the surroundings, resistance to the surroundings, in this case is equal to our convection, which is 1 over h bar times, what's my surface area that I should use? Again, we've picked that vector from the center line out in one direction, so it's crossing just that one top surface. So that's W times L again. Right? So we can now take the ratio of these two things, and we end up with Biot number is equal to, let's see, thickness over 2. Here we have 2WL H bar, and here we have KWL. That simplifies down to Biot is equal to thickness H bar over K. Right? So I can compute whether or not this can be approximated as a 1D extended surface if this number is small. Question?
Where are you getting the second 2 from?
The second 2. You mean here?
No, in the Biot number, the simplification.
Oh, let's see. Did I add a 2 in there? Thickness over 2, 2WL. Yeah, I think I added a 2, sorry. Let's be careful here. So that's thickness over 2 over 2. Right. This brings up an important point, which is, that's a very good question. If you're quibbling about factors of 2 in the Biot number, right, you're doing it wrong because the point of it is just to prove that a number is bigger than another number, right? So a factor of 2 shouldn't change your conclusion. But it's a good question. But ultimately, you're going to find like you might differ from your person sitting next to you by a factor of 2 or something. But if you're at this 0.1 threshold, right, you should be at things like 0.01, 0.001, right? Other questions on the Biot number? Okay, we're going to have to, go ahead.
It's not necessarily about the number of the equation, but at the beginning when you put the delta D conduction, is that in the Y direction?
Yes.
Okay.
Yep. Question was, is the delta t conduction in the y direction? Yes, it is.